Hello everyone, welcome to today's presentation on resonance in series RLC circuit. My name is V. Shanmugh Venkatsai and I will be guiding you through this topic. Resonance is a fundamental concept in electrical engineering that plays a crucial role in the design and analysis of various electrical circuits and systems. In particular, series RLC circuits are widely used in many applications including filtering, oscillations, and signal processing. In this presentation, we will derive into the basics of resonance in series RLC circuits, including the conditions for resonance, the resonance frequency, and the quality factor. We will also explore the applications of resonance in series RLC circuits and discuss some examples and case studies. By the end of this presentation, you will have a solid understanding of resonance in series RLC circuit and will be able to apply this knowledge to a real world problems. So let's get started. Introduction. A series RLC circuit consists of a resistor, inductor, and a capacitor connected in series. And the bullet points are resonance occurs when the circuit's impedance is at a minimum and resonance frequency is determined by the values of L and C. There is the series RLC circuit diagram showing resistor, inductor, and capacitor, and VR represents the voltage across the resistor, VL represents the voltage across the inductor, and VC represents the voltage across the capacitor. And V equals to Vm sin omega t, which is the source voltage. Resonance conditions. Resonance occurs when the reactance of the inductor equals to the reactance of the capacitor. That means XL equals to XC. And the equation for resonance condition is XL equals to XC. That is omega L equals to omega C. 1 by omega C. Bullet points about resonance conditions are: at resonance, the circuit's impedance is equals to the resistance. The current is at its is at its maximum value. Next, resonance frequency. Resonance frequency. The frequency at which reactance is equals to capacitive reactance is called resonance frequency. That means uh, at a particular frequency, the inductive reactance will be equals to the capacitive reactance. This at this frequency is called as resonance frequency. Equation for resonance frequency is Fr equals to 1 by 2 pi root LC. And derivation of resonance frequency equation. This is the derivation for resonance frequency equation. As we know that at resonance condition omega L minus 1 by XL minus XC equals to 0. So omega L minus 1 by omega C equals to 0. That means omega L equals to 1 by omega C. So omega square equals to 1 by LC. Also omega equals to, we know that 1 by 2 pi F. That is F equals to 1 by 2 pi omega. Substituting the values, we get F naught, that is Fr or resonance frequency, which is equals to the 1 by 2 pi root LC. Impedance at resonance. The impedance of a series RLC circuit at resonance is equals to the resistance value or Z equals to R. This is the minimum impedance condition. Derivation of impedance at resonance. Total impedance of series RLC circuit is, as we know that Z total equals to R plus Z in ZXL minus ZXA. Taking Z common, Z total equals to R plus Z of XL minus XC. At resonance, XL equals to XC. So the impedance now reduced to R. At resonance condition, we get the impedance minimum value. Current and voltage at resonance. At resonance, the current is at its maximum value and the voltage is at its minimum value. As we know that at resonance, the impedance is at its minimum value, and we also know that the current is inversely proportional to the impedance. So, as impedance is at its minimum value, current will be at its maximum value. And we also know that the voltage is directly proportional to the impedance. As impedance is at its minimum value, voltage is also at its minimum value. Since the current flowing through a series resonance circuit is a product of voltage divided by impedance, at resonance, the impedance Z is at its minimum value equals to R. Therefore, the circuit current at this frequency will be at its maximum value of V by R. Since I is maximum, V by R is also the maximum value, which is equals to the V by Z. Power factor at resonance. Power factor is defined as the cosine of the angle between the voltage and the current. Formula for power factor is calculated as the ratio of resistance to the total impedance. But here the total impedance is equals to the resistance. Hence, the power factor is the ratio between the resistance to the resistance, which is equals to the 1. The power factor of a series RLC circuit at resonance will be 1 due to the presence of only resistance as an effective impedance. As there is no reactive impedance inductor and impedance capacitor, the effective impedance is resistance. Derivation of power factor equation. Here is the derivation for the power factor equation. As we know that cos pi equals to R by Z. Z is equals to root of R square plus XL minus XC whole square. In resonance RLC circuit, we know that XL equals to XC, which is uh, omega L equals to 1 by omega C. The resistance is minimum. Hence, Z equals to root R square plus XL minus XC is 0 square. So Z equals to R, hence cos pi equals to R by Z, which is equals to R by R. Hence cos pi equals to unity. Quality factor at resonance. The quality factor is defined as the ratio of inductive reactance to the resistance R of the circuit. The quality factor is defined as simply the ratio of inductive reactance to the resistance. Fr equals to 1 by 2 pi root LC, which is the resonating frequency. Quality factor is the inductive reactance by resistance. Inductive reactance is omega L, which is 2 pi F into L by R equals to 2 pi into 1 by 2 pi root LC. As we know that resonance frequency is equals to the 1 by 2 pi root LC. Here F is taken as 1 by 2 pi root LC into L by R. And root L will get cancelled, we get and we get the quality factor is equals to the 1 by R root over L by C. And here are some graphs which are related to the resonance. The first graph represents between the current versus frequency at resonance. As we know that the current attains its maximum value when it hits its resonance condition. And the second graph represents the graph between impedance versus frequency. The impedance graph gets its minimum value at resonance frequency, and before resonance frequency and after resonance frequency it will get increases. Applications in resonance in series RLC circuit. Resonance in series RLC circuit is used in various applications. It is a very useful application for in our day-to-day life. This including filters, example band pass filters, and oscillators, example which are LC oscillators, which are highly used. Tuning circuits, example radio receivers, and medical devices such as MRI machines. Many more medical devices contains this resonance in series RLC circuit. And what we have discussed is about resonance in series RLC circuit is an important concept in electrical engineering. Summary bullet points are: resonance occurs when XL equals to XC. Resonance frequency depends on L and C. Current is maximum and voltage is minimum at resonance, and impedance is also at minimum. Thank you.